Okay, let's move on to problem 49, and like problem 40, this is about polynomials. So the first part of the question is the set of polynomials here, which we can establish using this, a linearly independent subset of the space of quadratic polynomials. And if not, part B, if not, express one of the polynomials as a linear combination of the other two. So let's start with problem A, or part A. So the first step is to formulate the problem as a linear algebra problem. Anyway, this set of polynomials will be a linearly independent subset of the set of quadratic polynomials if there are no non-trivial values of the parameters a, b, and c, for which the linear combination of the polynomials here is the zero polynomial. Well, we can establish these parameters using this, and anyway, this will be the case if all the will be the zero polynomial if all the coefficients of powers of x in this expression are zero. So we can extract those coefficients using this. And they are three linearly, or the left-hand sides of three homogeneous linear equations for the three parameters. And so to handle those, we need to extract the coefficient matrix, which is this, done using this, and we want to look at that as a matrix. And there it is there, and we need to calculate the right-hand side of the equations, which of course in this case will be 0, using that, and then view it as a column vector, like so, and then form the augmented matrix by joining this column onto the three columns of the matrix. And we can do that using this here. And we can see that it's been done correctly using this. So let's do the row reduction now on this matrix. So we can see that we want to add the first row to the second one to get the new second row, and we want to subtract twice the first row from the third row. So we do that using this, and then visualize the new augmented matrix using that, and we can see that we've got zeros in the first column under the diagonal. Well, now we want to go on and do the same thing with the next phase of the row reduction. So we want to add 3 times the second row to the third row, leaving the first 2 rows unchanged. And we get that. And we can view the matrix using that, and we can see that the bottom line is all zeros. So in fact there are non-trivial solutions, and therefore the polynomials are linearly dependent, and thus not a linearly independent subspace of the space of quadratic polynomials. So let's go on to the second part, and so let's try. So we want to express one of the polynomials as a linear combination of the other two. So let's pick the third polynomial and try to express that as a linear combination of the first two, and that will be the case if we can find unique values of the parameters a and b, such that the a times the first polynomial plus b times the second polynomial minus the third polynomial is the zero polynomial. So now these are our parameters, and we want to calculate this will be the zero polynomial if all the coefficients of all the powers of x up to x squared vanish, and we can calculate those coefficients using this. And then we can calculate so these are three linear equations for two variables, and we can calculate the coefficient matrix using this, and there it is. So we can visualize that using that. And then finally we can calculate the right hand side vector by multiplying the coefficient matrix by the parameters and subtracting off the equations. And that's the right hand side vector, which we can express as a column matrix or column vector. And now to get the augmented matrix, we want to join this vector onto this matrix here as its third column, and that can be done using this and visualize as a matrix using that. So now we want to start the row reduction. So we can see that we want to add the first row to the second to get the new second row, and subtract twice the first row from the third row to give the new third row. So we do that, and we can look at that as a matrix, and we can see that we have indeed succeeded in getting zeros under the diagonal in the first column. And now we repeat the operation, and we need to subtract or add 3 times the second row to the third row, leaving the first 2 rows unchanged. And we can visualize that as a matrix using this, and we can see that indeed the bottom row consists entirely of zeros, and we now want to convert each row of the matrix into a linear equation. This is the back substitution. So the equation corresponding to the third row is identically satisfied. Anyway, we do that for each row by defining this vector here, which consists of the 2 variables or the 2 parameters and -1. And then if we take the scalar product of the second row with this vector, then that should give us the equation represented by the second row. And we can see that that's a very simple equation. It has the solution b equals 3, which we can check using this. And now the left-hand side of the equation represented by the first row can be found using this. So we take the scalar product of the first row with the vector and insert the solution for b, which we've just found, and that should give an equation for a, which it does, and which we can set equal to 0 and solve using this. So a is 1, right? And now we can check that we've got the right answer by simply taking the polynomial that we started with and then substituting, in other words, the linear combination of the first 2 minus the third polynomial, and then insert the values of a and b that we've found, and the result should be 0, which it is. So that's the end of that problem. Well, the last problem on the list is quickly dealt with. This is problem 30. So it's kind of abstract problem, but so we've got a set S v of n little n vectors v1 up to vn, and that is supposed to be a linearly independent subset of a vector space V. Okay, so starting at the origin, we set off in the direction of V1. So this could be in a multi-dimensional space. And we do that for a time t, and where we'll have reached some point on the vector V1 relative to the origin. And then after that time, we head off in the direction of V2 for a certain length of time, and so on. And the question is it possible to return to the origin? And it says you may walk any distance you like along the n directions, but cannot retrace your steps. Okay, so the answer is, suppose we proceed in the direction of each vector for n positive time intervals, t1 up to tn. Then at the end of our process, our position relative to the origin will be t1 times v1. That's if we allow these vectors to represent velocities. And then we plus t2 v2 plus and so on up to tn vn. Well, if this gets back to the origin, then in fact we've found a non-trivial linear combination of the vectors, which is the zero vector. And this, of course, implies that the set is not linearly independent. So the answer to the question is no, we can't get back to the origin using this set of vectors.